7374, looking at slope fields. So a slope field is a way of showing information about a function, but looking at its derivative at a variety of points. So part number one, let's look at the differential equation given by dy dx equals 2x. What does each dot on this derivative graph represent? We'll come back to this question, and maybe it's a little bit out of order. It's referring to this question number 3. You've had graph paper before, x-axis, y-axis. Maybe you can even remember into pre-calculus, you also had those three-dimensional graphs, x, y, and z-axis. You can graph on those as well. We're looking at this graph that has those dots on it in order to draw one of these slope fields. So we're using the derivative. The derivative of this function is equal to 2x. I don't know a lot about the function. What I do know is that its derivative, dy dx, is equal to 2x. So at any point, this is how you would figure out its instantaneous rate of change, its slope. So at the point -2, 2, I'm going to plug this point into this derivative we have up here. And what this derivative is saying is it doesn't matter what the y value is. The derivative, the slope, is 2 times the x value. So I look over here, 2 times that x value would be -4. And to keep going with this, my next point is -2, 1. So I'm going to plug this into my derivative equation. My dy dx equals 2 times x. 2 times -2 is, again, -4. Seeing that? What's going to be the slope of this next point, -2, 0? -4. How about the next one? -4. Now we have to slow down. Next point is -1, 2. Plug that into our differential equation up here. What is going to be the slope at this point? -2, -2, -2, -2. All of them have the same x value. They all have the same slope. Going to the other column, what is going to be the slope at the point 0, 2? So 0, 0, 0, 0. One more set of points. What's going to be the derivative, the instantaneous rate of change for all these points? 2. Okay, so now we're going to take this and we're going to put it onto this kind of like a dot graph for the slope fields.
So is this finding the slope of a surface?
The slope of a graph at a specific point. And so let's go and start putting these in there. At -2, 2, -2, 2, the slope is -4. And as best we can, we're trying to, like, at this one point, draw a very small segment that has a slope of -4. This will be a little bit imprecise. Does it look like that has a slope of -4? No, a couple things wrong. It definitely looks positive and not negative, right? And if I were to continue it, it looks like this has a slope of +1. So it's way off. Instead, I want it to be negative. Does this look like a slope of -4? A lot better, right? It's definitely negative. And if I extended it, it looks like it's hitting like maybe a little bit, like maybe a slope of -2.5. So I'm going to try to make it look just a little bit better if I can. Say, okay, if I'm starting right here, a slope of -4 would go down 1, 2, 3, 4 over 1. So from here, I'm trying to aim at this point down there. It's going to be a very small little segment. There is my slope of -4 as best I can. If I had a ruler, I could bring that out to make sure that this is like a really good looking line. But again, I'm aiming for a slope of -4 over 1. So that's the first point. There it is. All right, so this isn't part of my slope field. I have the slope at that particular point. Now I'm going to do the next one. At -2, 1, the slope is -4 again. So at -2, 1, the slope is -4. So from here, it's aiming down 1, 2, 3, 4 over 1. So from this point, I'm aiming towards this one. Or in other words, these two lines should be parallel to each other. They have the same slope of -4. I've got a couple more points. -2, 0 has that same slope. -2, -1 has that same slope. So all 4 of those green segments have a slope of -4 as best I can. Next, at -1, 2, the slope is supposed to be -2. So -1, 2, I'm right here. The slope is supposed to be -2 over 1. So from here, I'm aiming down 2 over 1. So I'm aiming right at the origin. So a small little segment aimed at the origin. Negative 1 comma 1 has that same slope, so aim down 2 over 1, so I'm aiming at this point. All of these in this column should be parallel to each other. They all have the same slope of negative 2, so I have this whole column done. Next, 0, 2 has a slope of 0. This is an easy one. That's just a horizontal segment. All of these are going to be just horizontal. And in the next column over at 1 comma 2, we have a slope of 2. So over 1 up 2, the slope is 2. So up 2 over 1 or down 2 left 1, I'm aiming back at the origin. So there's my slope of 2. Down 2 over 1. So there's another one, and another one. So here is the start of my slope field. We're going to go a little bit further. We have this table to fill out. Could you figure out the rest of this column to the left? Aren't these all going to be the same slope of negative 4? So as best I can, I'm trying to draw them so they're all parallel. These should all have the same slope of negative 2. These have a slope of 0. These have a slope of positive 2. So I can finish off those columns. Again, it wants me to finish off the rest of this slope field. So let's go all the way to the left. What would be the slopes of all of these points that are farthest to the left when x equals negative 3? Negative 6. So from here, it'd be down 1, 2, 3, 4, 5, 6 over 1. So I'm aiming at some point down here. In other words, it is even steeper than the ones we had in the previous column. They're not quite vertical, but they are pretty steep. As we go to the right, when x equals 2, we have another column to fill in. What should be the slopes of all of these points? 4. So down 1, 2, 3, 4 over 1. I'm aiming at this point from up here. So again, it's just a little bit steeper. All of these are going to be parallel. And this is not an exact, precise science. How might you see something like this on an AP exam? Most likely it would be on a multiple choice. Which one of these slope fields is possible for this equation? Or given the slope field, which equation might work? All right, and then third column, if x is 3, these slopes are 6, so very steep, a lot steeper, not quite vertical, but pretty close. We have this slope field. So there are our slope fields. What does that do for us? Well, let's look at number 4. This is going to give us an idea of like what the benefit of the slope field does. It says sketch a curve that follows those slopes. How many curves are possible? How do you know? Okay, I'm going to put a point on there and say, what if we have a point right here? I could have picked any point, but maybe this is a point that was on the original curve. And what we're supposed to do then is kind of follow the pattern of what's happening here. So the slope at this point was down 2, so it's going to look something kind of like this. What's going to happen to the graph once it gets to the middle? Slope is 0, minimum, and then it's going to go to the right. What's going to happen? Start going up like this. It's going to do something like that. This is just kind of following like the pattern, like the trade winds of what are happening here. This is just one possible curve of what it might look like. How many curves are possible here? Like what if I had chosen a different starting point, like maybe like right there? Can you kind of like visualize what that one would have done? Maybe something like this, again, a little bit inexact. So there'd be an infinite many of them because I could pick any one of those starting points and it's going to have a slightly different pattern to it. Once you choose a starting point, it does its thing. So how many curves are possible? I would say an infinite number because there's an infinite number of paths. And it just matters which one of those you choose, and you're going to get a different path.
So is that like the justification you use on the...
It wouldn't be a justification question. Like this wouldn't be one that you could put on a free response because, again, it's kind of subjective in nature. Like I have seen in the past, like a very small slope field to fill out. I don't remember what year it was, but it was pretty easy. Like, okay, it's either positive, 0, or negative, depending on the differential equation that you were given, and then they could graph it off that. But like, if I look at my drawing over here, do I know for sure that this is a -6 slope and this is only -4 and this is -2? It's kind of hard to be that precise. And then I wouldn't have to justify anything. It's just looking at it and interpreting it. What I want you guys to spend a little time here doing is number 5. It says, find a general rule for y based on your knowledge of antiderivatives. Does this support the curve you drew in question 4? In other words, the very beginning, we had dy dx is equal to 2x. So we're using that again. Dy dx is equal to 2x. Knowing what you know about antiderivatives, can you take this back to the original? This is their differential equation. This is what the derivative is equal to. Can you try to find a rule, a formula for the original equation? And does that make sense based off of the slope or the slope fields we have here and a couple of these slope curves that we actually drew? So I'm going to give you a little time to see what you can make sense of that. All right, lots of different ideas on that. What you're going to want to do in this one is split these variables. On the left, we have dy over dx. It's not like totally mathematically correct to say to multiply by dx, but it works for all intents and purposes. So then we could say dy is equal to 2x dx. I don't really want these dy and dx's in there. So if I think mathematically, how do I undo a dy dx? Take the integral, integrate it, take the antiderivative. So we're going to integrate both sides. And what's interesting is on the right side, you're integrating with respect to x because it says dx inside of this integral. So what is the integral of 2x dx? Almost. Plus c, right? It doesn't have any bounds on it. So it's not a definite integral. It's an indefinite integral. So we have the plus c. What's the integral of dy? It's like a 1 there, so it becomes 1y. And we could put plus c. But if we have plus c on this side, the c values wouldn't necessarily be the same, but I could subtract this constant from that one, just get some other constant. So when you're integrating both sides, you don't have to put a plus c on both sides. Here is what our differential equation gives us as an original. Does this equation correspond to our slope field up there? Y equals x squared plus c. We know it's a parabola. It's a parabola opening up. Plus c, it could be shifted up by 1, down by 20, or whatever. It shows us all of the possible functions that would be associated with this differential function. So slope fields give us a general idea of what a graph is going to do, what it's going to look like. It's kind of open-ended unless you have a specific point that you're supposed to put on there. Go to the page. Slope fields are one of those topics that have only been in the AP curriculum for, I don't know, like the last 10 years, which seems like a long time, but in the scope of like math and like the AP curriculum overall, it is kind of a shorter time. We're going to say slope fields are a graphical representation of a differential equation that allows us to visualize the family of solution curves. So when we do all of those small little segments that have the specific slope, we have a lot of potential graphs that are in there. That was a very basic one that we just did because that derivative was only in terms of x. Sometimes it's going to be in terms of both x and y, which will make it look a little more unique than what that one was. But it gives us a graphical representation of what's going on with the potential original function. So we did slope fields. We did one example of a slope field. Sometimes we're going to be looking at those slope fields and turn them into a solution curve. So we had all those potential graphs that looked like parabolas. We didn't know which one could have been an actual one. We would have needed more information. But when you're given more information, like an initial condition, like saying it has to go through this point, that'll turn into a solution curve. It has to pass through that initial point. What's going to happen sometimes is you will have a differential equation and you plug in an x value or y value and the slope is undefined, then don't draw anything there. It might mean there's a vertical asymptote there, but it's not actually part of the graph, so we're not going to draw anything anytime that the slope is undefined. Okay, so these are our main points. Check your understanding. So on the first page, we had one where the differential equation dy dx was equal to 2x. So all those columns were the same. The derivative was only in terms of the x value. Now dy dx is equal to negative y, which means the x value doesn't matter for the slope, for that derivative. It's just the y value. I'll help you with one. If y is equal to 2, y is equal to 2 for all this entire top row up here, what would the slope be equal to? Negative 2. So right here, I'm going to say it's a slope of negative 2. So I'm aiming down 2 over 1. So I'm aiming right at that point. Try it again. Aiming right at that point. And all of these along the top row are going to have that same slope of negative 2. All of them are going to be parallel to each other. Can you try to fill out the next couple rows? So the derivative at that point is going to be the opposite of the y value. The y value is 1. So the derivative right there is going to be negative 1. Here, you want your slope to be negative 1. Here, aiming down 1 over 1 to the end of that point. You can have your slope. So this is the way that our differential equation is defined. So at this point, when the derivative at the point negative 3 times 1, is going to be take the y value and make the opposite. So the opposite of that is negative 1. So again, down 1 over 1 means so once you have it, it looks like you kind of see some patterns, some waves. You can kind of see how the original graph would have been trending. This is a graph based off of its derivative, but if we know something about the derivative, it gives us an idea of what the original graph is doing. It's not the most precise, but again, it gives us an idea of the trends and kind of what the graph is going to look like. In the next row down, in other words, when y equals 1, what are all these slopes going to be? Negative 1, so we're aiming, try to get a negative 1. And kind of imprecise, big thing is these are not as steep as the top row because those were negative 2. What's going to be the slope across the middle here? 0. So these are all going to be horizontal. That is defined. It's just 0. The next row across, these all have y values of negative 1. So their slopes are negative 1. So positive 1. So we're aiming up with a slope of 1 if possible. And then the bottom row, all of these are going to have a slope of positive 2. So aim up 2 over 1. So a little bit steeper. And there's our slope field for the first one. When you're ready, go after the second one. I'll help you just a little bit. Dy dx when we're at the point -3, 2. So I'm doing specifically this yellow point in the upper left-hand corner. I want to know, what does the slope look like at that point? So I'm going to plug the point in, -3 for x, 2 goes in for y. So that slope is going to be -3/2. Right? So the way the differential function is defined is that the derivative at any point is the x value divided by the y value. Since our x value is -3 and our y value is 2, at this point, the slope is going to be -3/2. So I'm aiming down 3/2. So from that yellow, I'm aiming at this point right here as best I can. And I'd recommend that you go like straight across in a row or straight down in a column. I'm going to show one more and show you how this one's going to be a little bit different. So at this blue point, dy dx, the derivative right there is at the point -2, 2. The differential equation says whatever point you're at, you take the x value divided by the y value. So the x value of -2 divided by the y value of +2 is -1. So at this blue point, the slope is supposed to be -1. I'm aiming down 1/1, aiming right at that point. Now, these two slopes are not the same. -3/2 is a little bit steeper. Hopefully it looks that way. But as we continue on the trend, you should start to see even more changes starting to happen with those. So see if you can finish off this first row and then start going through the other rows. This one will take a little bit longer because the derivative is in terms of both x and y. So you have to think about that a little more. Be as precise as you can, but don't get hung up because it is somewhat of an imprecise process. Because in these, all those rows are the same. Exactly. Every single point is different. So you just try to be as precise as you can, but recognizing that it's going to be not trivial, but it's hard to be terribly precise without. So this is a little steeper than that one, which is even like, so I can see the trend of how it's starting to flatten out a little bit, and that's what you want to be able to see. Multiply by x, multiply by y, you get y equals x. Integrate both sides, you get y squared equals x squared plus c. So then if you go to this side, you have y squared minus x squared equals c. No, it's plus b, so minus is an equivalent. You want to get this equal to 1, so if you divide everything by c, you have y squared over c minus x squared over c equals 1. You get an equivalent. All right, somebody help me with some of these. At this next point at -1, 2, what is the slope we're looking at? -1/2, -1/2, so a little bit more. What's the slope right here? 0/2, which is 0. So we can actually do that. 0 divided by 2 is 0. The next one to the right? 1/2, so up 1/2 or down 1, left 2. I'm aiming at that point, so it's kind of flat. And then I'm thinking probably 1 and then 2. So there's my top row. Each one of those is different. We went from a -2, gradually changed into a +2. or 3/2, I guess, 3/2, 3 over 2. Next row down, -3, 1. So at -3, 1, it would be -3 over 1, so -3. Down 3 over 1, we're looking even steeper than the row above it. This point is -2, 1, so the slope is -2 over 1. Slope of this point is -1 over 1, so it's a slope of -1, slope of 0. And then there's a lot of symmetry side to side, isn't there? Like these negative slopes become positive slopes on the other side. Sometimes people can pick that up really quickly, and that helps them with their graph. Sometimes it takes a little bit longer to pick up the patterns. There's a lot of dots here to fill out. And what I'm seeing is, yes, it is starting to level out. So what I see on the left is kind of reflected across, something kind of like that. And you can see how I'm not taking a lot of time to make sure it's absolutely perfect. Jared, put your phone away. Next row down, all of these y values are 0. So when you do x divided by 0, what's happening for all of these? Undefined, not horizontal, not vertical, although there might be some kind of vertical asymptote there. We don't know, but undefined right here. There is no slope right there, which might mean that the graph is undefined there. Might mean that there's a sharp turn right there, but the derivative is undefined. We know that. As we go down to this next row, at this point we have -3, -1. So -3, -1, that's -3 over -1, which would be +3. So up 3 over 1, I'm aiming at that point. -2 over -1 is a slope of +2 going towards that point. This is going to be a slope of +1, a slope of 0, -1, -2, and then -3. Again, I'm starting to figure out some patterns. I can go a little bit quicker. Just like left to right had mirror symmetry, it's like a reflection. Can you see how top to bottom has that same kind of reflectional symmetry? Like what we have on the top is reflected on the bottom. So this bottom row, -3, -2, slope is +3/2, up 3 over 2. I'm aiming at that point. This would be -2 over -2, which would be a slope of +1. -1 over -2 would be +1/2, so up 1 over 2. It's a little bit flatter to 0. And then something kind of like this. So here is a slope field. If I got the ruler out, I could verify how precise I was. I don't think that's really necessary. This is a good enough slope field for what we're looking for here. Question number 2 builds off of this. It says, sketch the particular solution to dy dx equals -y. That's this slope field that passes through the point 0, -1. So what it says is, you know 2 things about the original function. You know, this is its differential equation. This is the slope field for that. And the original function has to go through the point 0, -1. It has to go through that point. Now, what I'm supposed to do is kind of follow the trend of what's happening. This one had a slope of -1, so it's going to go up. And then eventually it's going to be 0, so it's going to level off. I think it's probably a horizontal asymptote as we go to the side. And then as we go this way, it's going to level down a little bit. So this would be a particular solution if it goes through the point 0, -1. We also could have gone through, like we could have picked a different point. If they had given us like -2, +2, we could have done the slope through this point. What I want you to do is do the same question for the other slope field. So put a particular point, a specific point at 0, -1. And then can you draw a path of what that one is kind of doing, what it kind of looks like? Zero, -1. So it's going to come down. Looks like it's going to come down, maybe do something kind of like that. Let me go back to the first page, and I have a couple questions I'm going to ask about this one related to the first one as well. Here's our differential equation. Here's the slope field all graphed out. Charlie, put your phone away. Is this original one a function? Would it pass the vertical line test? Yes. Do you think this one represents a function? Would it pass the vertical line test?
With that solution.
Yeah.
But there are solutions that aren't there solutions like that where.
Do you think that there's probably something, while this is happening, something else happening up here doing the same thing?
There is a solution that could do that.
Oh yeah, definitely.
Right? So like when x is 0, we have either this trend or that trend. It's quite possible that there is another graph going on up there. How about for this one? Do you think this one is a function? Would it pass the vertical line test? So you've got this going on. What about if we picked a point up here? Would this be going on like kind of looping up instead of down? So it might look something kind of like this. Would that be a function? No. Right? So maybe what we're working with here aren't always going to be functions. We prefer functions. It's nice when they pass the vertical line test when each x has at most one y value. But some of the graphs we're going to look at will not be functions. We can still find out things about them. It's just kind of broadening what we can look into. All right, so question 3, this is getting into a potential AP test question. You're given this slope field. So they figured out everything for you. Very precise from them. Awesome. And they're saying which one of these functions could have this as its slope field. So if I were to pick a point and say, all right, like let's follow the path, what's going on, maybe it's going to do something kind of like that. Or if I was further to the right, maybe I could say it starts right here and it does this. Right? I'm just following like one of those trends of what's happening and saying, well, which one of those graphs could it be? Look at the options. Like again, I'm just like kind of like grabbing someone saying, okay, this is what it could look like, or this is what it could look like. Are there any of these that you say like there's no way that the original graph could give this kind of a slope field? X squared, definitely no. Agree? Like a hard no on that one. What is your next most logical one to say? It's probably not this one either. Sine of x, because sine would have to go up and then start coming back down before we get to that 3, which is about pi. It would have had to come back down by then. So it's not going to be sine of x. It's either going to be one of these two. Y equals e to the x. Do you remember what that graph looks like? It's an exponential function that does something like this, right? Is that what we're seeing over here? No. This is a log function. Remember what log functions look like? Like that. We have this very steep part of the graph right here. There's a vertical asymptote because you can't put a negative value in for x. You can't take the log of it. So as you look at this graph, can you kind of see how this is building into a vertical asymptote at x equals 0? And it's kind of trailing off. It's not going as fast. I would say the best answer for this one is going to be C. Definitely not B, definitely not D. And based off of the information we're given, C looks much more appropriate than letter A does. All right, number 4. Number 4 is getting into section 7.5 and 7.6. So we haven't done this yet, but this is probably like one of the biggest takeaways out of this section and these couple sections in here. We're given a differential equation right here, and we're supposed to write the equation of a line tangent to the original function at x equals 3, given this information, and use that to approximate f of 3.1. Lots of stuff right there. Lots of stuff given to us. I could draw a slope field for this. Good news is, just did it up here. Right? dy dx is equal to x over y. That's the same thing that we're looking at down here. Does that slope field help me necessarily? I don't know. Not necessarily. I don't really think so. But what I am going to do is I'm going to find, since like whatever the graph looks like, I want to get a tangent line. I want to find what is the slope of this original curve right there. Right? Like, to write the equation of a line, you need to know the slope and you need to know a point it passes through. So what is the slope? What is dy dx at? What does this mean as a point? 3, 4. So what is the slope at 3, 4? Plug it in, 3 over 4. The x value divided by the y value. There is our slope. What point does this tangent line pass through? 3, 4. Right? It's got to go through that point. So can you write the equation of the line that has this slope and goes through that point. So here's the equation of our tangent line. What does this mean to us? Well, going back up to my slope curve, if there was a point at 3, 4, it would have been up here. And if I like drew out what it was doing, so maybe it was doing something kind of like this. So I want to make sure I hit that point. So maybe the original graph was doing like this, using my slope field as an idea of what the graph looks like. If I wrote the equation of that tangent line, the slope right there is 3/4. It goes through that point 3, 4. That's what we're dealing with in this problem. Okay. Use this to approximate f of 3.1. So what we know is when you find an x value very close to that point that we're drawing the tangent line through, so again, 3, 4, we think the graph looks something like this. Here's the equation of my tangent line. If I go just to the right by 0.1 to x equals 3.1, like right here, the tangent line approximation is very close to the actual curve. If I get too far away from that 3, 4 point, my approximation isn't guaranteed to be very accurate, but I'm only going right by 0.1. So plug 3.1 in for x. (3.1 minus 3 is 0.1. I can do this math. 0.1 times 3/4 would be 0.3 over 4. And maybe you're saying, okay, 0.3 over 4 I'm not very familiar with. So another way to consider that is it is 3/4 times 0.1. As a decimal, what is 3/4? So what's 0.75 times 0.1? So if we add 4 to both sides, then y equals 4.075. So the y value did not increase by very much. When x was 3, y was 4. So what we're saying is if this trend is true, then when x equals 3.1, y would be equal to 4.075. Not a very big increase, but it did increase and increase by approximately that much. So this is using the differential equations. So 7172, we had, let me go back real quick. We had the problems where we had the very inversely, very directly. We had the problems where we're trying to verify whether or not the solution works for a specific differential equation, something that might look like this. We got into some slope fields. And I'll say like the biggest meat of this section is going to come into a problem like this. Let's get briefly started on 7677 today. Again, here's where like the meat of the whole sector, the unit's going to be. Okay, so here is the gist of a problem like this. Find the particular solution to the differential equation that looks like this. They're telling us a couple things, or asking for what is the equation of the original function, given that the derivative in general looks like this, and the original function passed through the point 1, 7. So over 1, up 7. I know this is a clue. I know that the graph has to go through that point. And I know that the slope for any point has to follow this general pattern. We're going to do something with this. Now, this first step is very simple, yet very important. And you'll probably see something like this on an AP free response question. One simple point, maybe the easiest point you can get in free response, is when you're given a differential equation like this, you want to split the variables. Get all of your x's on one side, get all of your y's on the other. In this case, it's as simple as moving the dx to the right side, like multiplying by dx to get out of the denominator onto the right side. So we would have dy is equal to 4x dx. So it's the separation of variables. Sometimes you might have like some y stuff on the left. You might have a y in the denominator. You might have an x in the denominator on the right, but all of the y's on one side, all of the x's on the other, and make sure that the dy and dx are not in the denominators. Once you have these separated, integrate. That's how we get rid of those dy's, and it tells us what to integrate with respect to. So on the right, when we integrate this, not derivative, but integrate, find the antiderivative, what would be the integral of this right side? That plus c is massively important. It's an indefinite integral. And on the left, what's the integral of dy? Y. Again, it could be y plus c, but we would have subtracted that to get it to the other side, which would have wrapped into another constant. So we just have to put the plus c on one side. This is the general solution. Now to get more specific, like which y equals 2x squared should we graph? Like here's y equals 2x squared, here's y equals 2x squared, there's y equals 2x squared, all plus or minus some different number. Well, we have to take the one that goes through the point 1, 7, this point. How are we going to figure out the c value? Plug it in. Plug it in. Plug it in so we can find the specific c value that's going to make this y equals 2x squared go through the point 1, 7. Plug 7 in for y. Plug 1 in for x. So c equals 5. So our answer to this question, y equals 2x squared plus 5. This answer satisfies the two requirements, or these two clues we were given. Let me ask you, this yellow answer, what is the derivative of this? What's dy dx equal to? 4. Check, that's what it's supposed to be equal to. Does the point 1, 7 work on this one? If you plug 1 in for x, does y equal 7? Check. That is our correct answer. So again, this is a very important problem for us to know how to do something like this. Split the variables, integrate, plus c on one side, plug in your value, and you can get the initial equation.